Hi, this is episode 1 of Data Every Day, a series where we'll be looking at various Kaggle datasets and running machine learning algorithms on them. So basically what we'll do is we'll find a dataset, we will process the dataset, feed it into the model, which we will train, and then make some predictions on it. Hopefully some visualizations also to see how the dataset is performing with our model. So I found this dataset on Kaggle.com, League of Legends Diamond Ranked Games. So I don't know if you guys play League, but I've been playing League for the last 9 years now. No, probably 8 years. And so basically, this is doing is it's giving data from the first 10 minutes of the game. And if we look at the dataset, you can see it has a bunch of feature columns, but this here is the label column, which we're trying to predict. Either blue wins or blue does not win. 1 being a win for blue. 0 implies a win for red, but there's no duplicate column for that. So if you look at the summary, we have 40 columns total, and this is only, I think, this is just a preview of it. But anyway, we'll start up by opening up a new notebook and write Python. And I think we will use neural network for this. Even though it's not that complicated of a data set, and we could probably fit a great model using a simpler model, I wanted to do neural network basically just because they're cool, and I'll have plenty of other videos about other models. But so we start LoL win prediction. Okay, so we'll start off as usual, import numpy as np. Whoops. Import pandas as pd. Oh, sorry. LoL wins data set. Whatever. Okay. So yeah, okay. We're gonna import TensorFlow. And from TensorFlow, we will import keras.layers. I'm not sure if we need anything else. I'll look it up. But so we're going to get started and just preview the dataset. So the good thing about Kaggle is if you start a notebook on one of the kernel, you start a new kernel on a Kaggle dataset, it comes preloaded into the notebook. So it's very easy to reference the data. You don't have to load it in. But we can just copy the file path here, and we can say, I'm forgetting the way to get data in. So, oh right, it's read from CSV. Okay, so this is a CSV file, I believe. If we go back to the dataset, you can see, yes, it's .csv. So we will call it data frame, or we'll just call it data, is equal to pandas.read CSV, and we'll just paste in the file path. Oh, wait, in quotes. Okay, and basically this is going to be just loading in dataset. Okay, and PD is not defined. Oh, we didn't run this, of course. Oh, I must have gotten something wrong. Keras layers API from TensorFlow.keras. Import layers. That's what it was. From TensorFlow.keras import layers. Okay. All right. That's loading. Just give it a second. Okay. And now, what is wrong? Oh. Let's just look this up. This is a learning process for me too. You know, I haven't gotten this error before. We're trying to see exactly what it is. trying to input zip is corrupted. Let's try it again. Don't know how that would work though. No. Look at this. Oh, I copied this? I wasn't looking. This is the actual file path. Okay. Alright. So now we have our data set. So we can check it out with data.head. And you can see, okay, so we have, we can actually, here, data.shape. Oh. Alright, so we have 9,879 training examples and 40 columns. Now, you can see right away this game ID feature is not helping us with anything because, first of all, there's no way it's going to help us predict the win, whether or not the blue team won. It's just sort of a nonsense column. So we're going to remove it by saying data.drop game ID axis 1 and in place, what is it, in place one word, true. And now if we check the shape, we have dropped one column. We check the head again, and you can see game ID has been removed. So if in case you don't know, we use axis 1 to denote the horizontal axis. If we hit axis 0, it would be trying to drop it from the vertical axis. In place allows us to call it right on the data set. If we had in place false, we'd have to store it into a new, store it into a new variable. Okay, so next we're going to have to clean up our data set a little further, because I don't know if you can see this right now, but actually I think let's get Seaborn in here. Let's import Seaborn. Import Seaborn as SNS, and I'll just run that whole thing again, even though it's going to load everything. SNS dot. Okay, wait. How do we do this? I'm trying to get the heat map. We want to see the correlation. Seaborn. Okay. So Seaborn dot heat map with the data. Let's just see what that does. Dot heat map data. Okay, so this is not helping us. What are we trying to do? How do we get the correlation matrix? Correlation matrix Python Pandas. Oh, it's really just df.correlation.core. Alright, awesome. So data.core. Okay, here we go. Now, this is showing us which data is correlated with other data. The light colors is representing high correlation, and the darker colors is representing, sorry, not high, positive correlation, and the darker colors are representing negative correlation. So, as we can see, the first half of the features is all blue stats. So there's a blue team and a red team in League. And the second half is all red team stats. So as we can see, the blue team stats are positively correlated with the other blue team stats. You see? So, I mean, we shouldn't worry about blue wins shouldn't be in there. Blue wins isn't really what we're looking at. Let's just separate blue wins real quick. So we can call it y is equal to data blue wins. Now we just check y. Yeah, y is our label column now. And I want to shuffle the data. let's shuffle it. Let's just randomize the order. Pandas shuffle rows. Oh, right, this is the one right here. So the reason I want to shuffle the data is because just to eliminate any possibility of some underlying bias in the data just from the way it was entered. Probably not a problem, but it's good to do anyway. So this should do it. This is, what is the frac? It's good to know what this does. So let's look it up. Pandas shuffle rows. Sorry. Okay, sample. So pandas sample. Dataframe.sample. And let's see. So the fraction of the axis items to return. Right. So 1. This is going to be a value between 0 and 1. 1 means let's return all of them. So what this is doing is it's sampling 100% of the data set. And it's going to reset the index because the indexes get switched also. So reset index brings it back down. So if we run this, and then we run this, now it's been shuffled around. Good to go. Sort of unnecessary, but also not too bad. So now we can do this. Okay, now we have to drop off. So we'll say x is equal to data.drop blue wins. Axis equals 1, in place is true. So now x, what? Oh, not in place. In place false this time. See? But I already dropped it. Okay. Well, let's reload it just so you get the sense of what I'm doing here. We're going to load in the data. Look at the shape. There's 40 columns. And if we look at it, we want to get rid of the game ID and we want to separate blue wins off the data set. So we're going to drop game ID right away. If you look at it now, game ID is gone. Then we're going to shuffle the data just for safety. Look at it again. It's been shuffled. Now we're going to save the blue wins column into Y. And if you look at Y now, you can see just a label column. Then we're going to store the data with the dropped column into X. Like that. Okay, now if we look at X, I don't understand. What did I do wrong? Well, obviously, we could check data now. I have it up here. Hold on. Blue wins is still there. So it didn't work. I don't know why. This will tell us if it's a data frame or not. It is not. So somehow it's not actually returning the data set. If we do this, there it is. Why can't we store it next? Oh, okay. It worked. Alright, so now you can see X is basically all our features without the label column, and Y is just the label column. So we've properly separated our data straight from the CSV file. So now we're going to create a correlation matrix from the data, and we're going to make a heat map from it. So all that does is show, oh my god, not data, X. There we go. So this shows the correlation between features. Again, if it's a light color, it's positively correlated. If it's a dark color, it's negatively correlated. So as you can see, as I was saying earlier, these blue features associated with the blue team are positively correlated with the other blue features, and the red features are negatively correlated with the blue features. You see what I mean? Let me rephrase. Blue is positively correlated with blue. That's what we see, this big white square here. Red is positively correlated with red. That's why we see this white square here. Blue is negatively correlated with red, which we see right here in the dark square. And because it's a symmetric matrix, because the covariance has to be, it's equal on both sides. Red with blue, blue with red, it's the same thing. So right here, these are both, it's a negative correlation. Right. So basically what we see about this is that we have some redundant features. Because if all these features are predicting the same thing, like basically what it's saying is this is all sort of one feature. You see, because it's positively correlated, they all go up together, or a large number of them go up together. What it's saying is when the blue total gold is high, then the blue total experience is high. That's why I have a little white dot there. And you can actually see the blue deaths has a dark line straight across, because deaths is like indicative of losing, whereas all the other features are indicative of winning. So what are we going to do about this? Okay, well, first of all, we can actually see straight away some of these are completely redundant. The blue experience difference and the red experience difference. Wait, is it there? Oh, wait a minute. It looks like they may have... No, yeah, here it is. Why is it only showing on this side? Am I missing something? Red gold diff. Oh wait, no. Yeah, okay, so it looks like all the redundant features were stripped from the dataset. As I worked with this one briefly a few weeks ago, and at that time there were a lot of redundant features, but it looks like many of them have been taken away. So we should be good to go. I'm not going to stress the feature cleanup so much right now, but I might cover this more in a later video. I think in another video I'm going to try principal component analysis, which will basically group features by their correlation and create new features in a lower dimension. But since this really isn't a very large data set, so we're just going to go ahead and feed it straight into the algorithm. Alright, so let's start up our model. Before we do that, we have to cut our data set into a train and test set. So TensorFlow has a built-in validation split, so we don't have to separate our training data into a cross-validation set this time, but we're definitely going to have to separate into train and test. So let's make a variable called train test split, and this is just going to be the percentage of our data set that will be trained. So we can do 70% or 80%, it doesn't really matter. Let's stick with 70. And then num examples, that's going to be the length. No, we can do x dot shape and the first the first one. So because x dot shape, as we saw before, is a vector of our dimensions, the first one is how many rows we have, the second one is how many columns we have. So when we run this now, it should be 38, 39. No, this is data. X dot shape should be 38, right? Okay. But so if we select the first element of shape, we're getting the number of rows. Num labels, no. we don't need to include that. This is a binary classification. We're going to be classifying based on just 0 and 1, so I don't see the point of doing the labels. However, okay, it's alright. So we have the number of examples. Now we need number of training examples, number of test examples. So num train examples is going to be num examples times train test split. This will take 70% of the training of the total number of examples as the number of our training examples, and similarly num test examples will be num train examples minus num examples minus num train examples. Okay. So I should just alright, now you can see. Oh, we have to floor function this. So we can floor, I think is it np.floor? And we ceiling this one. Okay. So, and cast as an integer. Okay, so if we look at that, 6915 plus 2964 is 9879. So yeah, so this is all our training examples, this is all our test examples, and this is our total number of examples. Alright, next we will just start up our model. So before we start, we're going to pick a loss function and an optimization function. So our optimizer is going to be Atom. TensorFlow Atom optimizer. So Atom is supposedly the most well optimized version of the, I may be wrong about this. I'm pretty sure Atom is really good for all neural networks, but I'm definitely not. Don't quote me on that. Basically, it takes in a learning rate, alpha, a beta 1 and a beta 2, where I think these scale the first and second moments. You know what? I'm not going to go into the math. I read the paper on this a while ago, but you can go check it out somewhere. Basically, it's just an optimization function. So it's like gradient descent, but like on steroids. Let's go ahead and grab it like this. We don't have to actually do this variable like this, but I like doing it because we can leave up the learning rate and tweak it if we like. So delete that, obviously, and run that. Okay, that's our optimizer. And for okay, so we're going to use sparse categorical loss because we're doing categorical classification. Sparse categorical loss. Or cross entropy, right? Okay, so this is our loss function. And we can just grab this, I believe. And now, alright, so we'll start up our model by saying model equals, hold on, TensorFlow model. You know, if you don't know, just look it up as you go. I just don't want to, Okay, it's tf.keras.model, and then right like this. Oh no, this is it right here. This is nice. Okay. So our inputs is going to be of shape. How many features are we putting in? 38, right? And to just test that again, we can look at the top, x.shape, 38 features, 9,000 training examples. No. That's total examples. 6,915 training examples. But our shape is 38, so a 38 by 1 vector. But I think by leaving this blank here, it makes it a vector. I'm pretty sure that's what that does. Please, by all means, tell me if I'm wrong about any of this stuff, because I'm learning about this just as much as you are. And so we're going to have probably 2 dense layers. We could do it with 1, probably. This is not that bad of a data set that we're going to need a complex model. But I think if we just do 2 dense layers with 16 nodes apiece, we'll get good results. So, right. Okay, so the way this works is we have our first layer here as an input layer, and then we feed it in at the to this guy, x. So this inputs gets put into a dense, fully connected 16 node layer, and then we're going to make a new one, which is we just pass the same. We're going to pass it back into to x again. tf.keras.layers.dense 16 nodes. Activation is ReLU, and here we pass an x. The outputs is going to be, it's going to take an x, right? And so it's going to be 2, because we're trying to classify between blue win or red win. And so let's see. This looks good. Softmax should give us a classification between 0 and 1. Remember, softmax is like sigmoid, right? Softmax function. Yeah. So it's a lot like sigmoid. It'll basically, the higher the error in the, how do I say this? What's along the x-axis here in this picture? We classify at the 0.5 mark. We don't have a skewed data set, so we can just leave it at 0.5. But what are we actually... Oh, right. This is the prediction. Okay, if our prediction is very positive, if I remember correctly, this is our theta, our weights, times our input. So if our weights times our input, sorry, dot product. So if they're very similar, if our weights and our input are, you can think of them as vectors in a way, pointing towards the same direction, we'll get a very high value here. If they're pointing in opposite directions, which would naturally mean a negative classification, y equals 0, we'll get a very negative value. Anything past 0 will become 1, or very close to 1, and anything below 0 will go to -1. Right, okay. I think sigmoid, the only difference is that it goes from 0 to 1 instead of -1 to 1, if I remember correctly. Okay, but so we'll use softmax, and I think that should be good. So we use our inputs layer as our inputs and our outputs layer as our outputs. So now if we do that and we hit model.summary, you can see we have 4 layers, an input layer, a fully connected layer, another fully connected layer, and an output layer. This one has input size 38. This has input size 16, input size 16 again, and then input size 2. So the total number of parameters we'll be adjusting is 930. So I think we're ready. We're going to compile the model. So this is keras.model, keras.model, compile. Okay, so we're going to pop this in, model.compile. And then, so our optimizer is going to be the one we had earlier, optimizer. Our loss will be sparse categorical cross entropy. Metrics, we can use, we could use accuracy, because the number of red wins and blue wins, actually, why don't we count that up? Easy way to do that. How do we sum in Panda? We sum across rows. Sum in Pandas. Dot sum. For the requested axis. Specify the axis. Okay, so y dot sum axis. I don't know if we need to write the axis. Okay, divided by y dot shape. Never mind. Divided by num examples. Okay, so it's about 50%. So because we have equal amounts blue wins and red wins, we don't need to use a different metric, such as precision or recall, or f-score. Accuracy will work just fine, because it's simply the number of successful predictions over the total number of predictions. Okay. So we can just take this stuff off, I'm pretty sure. Okay. So we compile it, and it looks like it's not defined. It might be like that, is it? Oh wait, no, it's keras. What is it? I had it here. This one. tf.keras.losses. That's the one. Right, of course. Accuracy is not defined. df.keras.metrics. Binary accuracy. Wait. Oh, it should be in quotes. Okay. Okay. So why don't we just make this easier to see? Okay, and it's compiled. So now we're ready to train it. So before we train, we have to actually create our dataset, our train and test. Because right up here, all we did was say the number of each. But basically, we're going to say xtrain is going to be equal to x from 0, these are rows, to num train examples, and all columns. Ytrain is going to be y.iloc, the same thing. Right. Now xtest is going to be x.iloc num train examples until num examples and all columns. Ytest will be the same thing. Okay, so, oh, too many indexers. What's wrong here? Let's look that up. iloc too many indexers. Hmm. Oh, I put too much. Oh, okay. It's because y is actually just a vector. So we can take that off, because we don't need to specify all columns. Alright, so now let's just briefly look through these. .head, and so, okay, this is 6,915 training examples, as we saw before, 38 features. X-test. This is 2,964 training examples, 38 features. If we look at our earlier values, where is it? Here. 2,964, 6,915. Perfect. Alright, so what do we do next? Okay. Alright. I'm pretty sure we have everything. Pretty sure we have everything we need. Just to look at this. You can see y is looking the same. Y is looking just as good. But just to make sure, there really shouldn't be a problem here. Everything looks good. Okay, so we can train the model. We have our x-train, our y-train, our x-test, our y-test, and now we will do model.fit. So where is it? Here, model.fit. Says, okay, we'll just take this. So model.fit. Our x is going to be what? X-train. Our y, y-train. Our batch size, we should specify a batch size. Batch size, let's make it 64. We could do 32, why not? Epochs, we also need to specify a number of epochs. We could do 300, just to start. So, batch size, epochs. Epochs will be verbose, we want to see what we're doing. Validation split. Let's see, we originally split it 70%, 30%. So, I think if we do another 20% of the 70%, that should give us a decent split. Validation data, we're not using validation data, we're going to split it instead. Shuffle true, this will, because TensorFlow has the shuffle feature, shuffling it at the beginning didn't really do anything, because it's going to do it anyway. But, that's fine. Class weight, no. Sample weight, no. Initial epoch, no. Steps per epoch, no. I think we're good here. I don't think we have to specify any more of this stuff. Okay, so let's just clean it up here. Looks a lot better. Okay, looks good. Let us run it. See how we do. Oh, I didn't run this. All right, we're training the model. The most exciting part of the job. Oh no! What's going on here? So we got another problem. expected float32 passed a parameter y, but we got auto of type string. Let's see what this says. I don't know if this is going to help. Essentially, it seems like there's a file type problem with y. I could see a few ways around this. I'm not sure exactly why this is happening, but I'm pretty sure if we converted it to a NumPy array, it would have a lot easier time. So we could just go ahead and do that. Xtrain equals xtrain to NumPy. Ytrain is ytrain dot to NumPy. I think that should. Let's see if that works. Oh no, it's giving us the same error, so that was not the problem. But it's a type error. Here, it's coming up for TensorFlow here. So let's see. The same issue. It's saying that we need, oh, this is a possible fix. I have a feeling that this problem is simpler than it looks. Let's take a look at what we did. So obviously we've run into a bit of an issue. Not to worry, we're going to figure this out. Let's just think about, okay, yeah, it's saying that it's expecting a float32, right? But it's saying that there's two errors here. No. It's getting a string. A string? Why is it a string? It's an int. I don't understand. Oh man. Let's take a look at this again. Let's take a look at this. This one here. No, not too many indexers. What happened? Still have that open? Let's go. This one. This is exactly the thing. So, look, he's getting the same exact file. saying that it's possible the loss function is wrong. Mean squared error. Oh wait, isn't this supposed to be like that? I'm not sure if it has any effect, but let's see. Oh, that was it. The problem is there's supposed to be a parentheses on the end. Wow, that's insane. All right, so we're training, and we're keeping an eye on the validation accuracy. We don't want the validation accuracy to be too far above the training accuracy, or we will have overfit our data. And you can see it is actually, it's going up pretty high. Oh wait, it's dropped? Oh, it's going all over the place. Let's just wait to see what happens. I don't think this should be too long. Run. Alright, we're more than halfway through. What a stupid error. I'll try not to forget that in the future. I wonder what it was trying to do without this. Okay. I should cut these parts out, right? No one wants to sit here to watch this go for an hour. Okay, we finished. So our total accuracy is 70%. Well, let's check our total accuracy. Model.evaluate. Oh, I think we have to score. What is it? What's the second? I'll just call it A, B. See what it is first. What? Wait. Data adapter that can handle. Hold on. Let's look up the function. Evaluate. Here it is. Model.evaluate. Oh, right. We have to evaluate on the test set. Okay, so this is the part where we see if it will generalize to new data. So it returns, what does it return? Returns a scalar test loss and just a loss. Oh, and then the metrics as well. So our accuracy was our metric, right? So we're going to do loss accuracy. Oh, on X test. Y test. Okay. We got an accuracy of 73%. Now that may look bad, but if you think about it, this is actually really good. Because League of Legends is a game where being able to accurately predict the outcome of the game is not easy. Because remember, this is only after the first 10 minutes of the game. There's such a thing as a comeback. And in 30% of the games, it's very likely that a comeback happened. So I was looking around at some of the other kernels and the other notebooks. And for example, let's look at this top one here. This guy, if we scroll down to the bottom, he got, where is it? No, where's his accuracy? This guy did a whole bunch of models on it. Okay, 72%. Oh, here they are. The highest accuracy he got was with logistic regression of 73%. 73.02. So if you look, we actually beat it. You know, I really think neural networks are amazing technology. They're just so good at detecting underlying trends. Like, it's so it allows for so much complexity to truly see the patterns in the data that other algorithms they can't achieve that level of complexity from what I've seen. Even though this is not a very complex data set. I mean, it was able to make quick work of it. So I think I'll stop the video here. It's been going 50 minutes. Let's take a break, come back tomorrow, and I'll have another data set ready. Alright, thanks a lot for watching, guys. I hope you enjoy the episode. I'll see you tomorrow.